Thank you for having me. So I abbreviated the slide title a wee bit, so it's now just Basil, or why you should have a build system. And I want to lead in with a bit of a story here. So flashback to winter 2015, the Angular team had recently decided to move everything over to TypeScript. And so winter 2015, we were sitting in Angular headquarters in Mountain View in California, is actual footage, sitting there shivering and moving everything over to TypeScript. So we thought, that's what we did, we poured everything to TypeScript. Now, porting to TypeScript was actually surprisingly straightforward for us, right? We had this, you remember that, we had the weird syntax that already contained type annotations in many places, and so we were like kind of already on TypeScript in a way, and so the port was not that hard. What actually turned out to completely kill Alex, Eagle, and me, who did that at the time, was fixing the build. So I have to motivate it a bit, because you would think, the build should be looking like this somehow, right? So you have TypeScript files, you have something, in this case it was a gulp file, and then you have JavaScript files falling out on the other side. And so you might look at this and think like, how hard could it be, right? And well, it turns out pretty hard, because in reality we had TypeScript files going into our gulp file, and then we had JavaScript files going into our build file, we had Sass files going into it, and then we had Dart files going into it, and there was a big, difference and variation in all these inputs and all these different rules, how they had to be treated. And then on the output side, so to say, it turns out, well, we wanted to produce ECMAScript modules, of course, but we also wanted to produce common.js, and we had closure annotated output, and we had UMD modules, and so we had all this variation in the output as well. And to implement all this stuff, what we had was this gulp file that was actually a lot larger than displayed here. So we had about 2,000 lines of code in this build system. We had about 100 individual tasks defined in the gulp file. These tasks had about 400 dependencies in total, so you can imagine that these were like quite a, a maze of dependencies. We had about a dozen tools that were being called, so from the TypeScript compiler, through bundlers, through closure, through, at that time we were still doing Dart, so we had that too. And so we had a whole bunch of various tools that were all having different command lines and different ways of how they would consume sources. And of course, this being gulp, the build was asynchronous, and it was concurrent at times, right? So you would kick off multiple processes running at the same time. And that actually, together with 100 tasks and 400 dependencies, led to a completely unchecked build. So what the things we were struggling with were that we had this build task that was supposed to produce a certain set of files, but then it didn't specify its dependencies correctly. So if you just ran it, then it would not produce the correct result. And so we had to rerun it and then manually run the other task before that, and actually reverse engineering across those 2,000 lines of code what the intended dependencies were and what the intended sequence of these builds was really hard. And we ended up in this situation because we probably lacked a bit of attention to this whole thing, but also there's nothing that keeps you from building a build file that is pretty bad. Right? There's nothing that keeps you from forgetting dependencies or from specifying tasks that, in this case, actually were running concurrently. So if one task completed earlier, the build might be incorrect because it picked up other files, stuff like that. Right? So really what we had here was a gulp file that consisted of spaghetti, and actually we mixed some broccoli into the spaghetti. So this is the broccoli build tool. You might remember that. It's actually good, right? Broccoli actually was a huge improvement conceptually, but the way how we forced it into our build really didn't make matters much better, I think. So yeah, spaghetti. It's actually not as nice as it looks in reality. Okay, so Angular's build was pretty bad at the time, right? So it was slow. We had to restart the build all the time. You had to run clean builds all the time if you change anything to be confident that what you're doing is correct. It was non-reproducible at times, right? So if you had concurrent tasks that were finishing at different orders, it was a mess, right? Or you would run a particular command and something hadn't specified correct dependencies. So it was buggy, non-reproducible. It was undocumented and pretty cryptic. So because we just wrote the build rules, we didn't actually leave big comments or something like that. You don't think about your build file as like a piece of software engineering where you would like write tests or something like that, and you should not, right? And so it was pretty hard to understand, hard to debug, and even harder to change ultimately, because once you have a system like that, it's really, really tricky to make changes. And so this was sad, right? So we were sitting there and we like tried to fix this thing, and it took us, what should have taken us a few days at most, actually took us 2 engineers, weeks to port all these things and fix them and make them a bit better. And I think we never really entirely succeeded, right? So we got it to a better state, but it was still kind of iffy. And you might wonder, okay, so maybe Angular is just a special snowflake, right? So maybe Angular is just this really weird project because it's a framework, it has more outputs and all this kind of stuff. And maybe that's the case. I think in our situation, the problem was a bit bigger than it is for most other projects. But in my experience, essentially every project I've ever worked on was actually a snowflake in this regard. And the interesting bit there is that all the snowflakes are slightly different, right? As we know, all these snowflakes are special in their own little special way, but the conceptual problem stays the same, right? You have some process where you take inputs, you produce outputs, and you have, in most situations, a very undefined system of how this works, and it can be buggy, and it can be non-reproducible, and can be non-incremental, and slow, and all this kind of stuff, and that's just super annoying. And this is particularly annoying for Alex and me because we had been at Google for a while, and being at Google for a while, we had worked with Google internal systems before that. And it turns out within Google, this problem had been solved, right? And we were completely aware of this problem being solved. And so we were just fighting with the lack of tooling that we had outside. So Google has this build system called Blaze and has built that a long time ago, actually. And I would say it's solving the problem. So it's fast, it's incremental, it's debuggable, it's reproducible, the builds are always precise. And so you can't run into all these problems that we ran into. The good news is that, as you probably all know, this has been open sourced as a tool called Basil. And so Blaze was apparently already taken as a name, so we had to go with Basil. But Basil is around, and you can use that. This is the homepage that's linked there. And talking a bit about Basil, why is it actually a good thing, right? So if you take a step back, your build system is essentially like a functional programming function, right? So it's a pure function that takes inputs and produces results. And Bazel implements such a functional system. And I'm going to talk a bit about how these things are actually, how these are advantages, what the functional programming brings us in here. So functional builds are builds where the build operation is a pure function of its inputs and just produces outputs. So it's hermetic, meaning only the inputs that are explicitly there will actually be readable and visible to your build steps. And that means also that your build operations cannot have side effects, right? So you can't create files outside in a different file system or read something from another place. And Bazel achieves that with sandbox execution. And the build function should also be idempotent. That means if you rerun the same build over and over again, you get the same result reproducibly. And they only depend on the inputs. And that's usually beneficial to debug your build operation, right? Also in Bazel is that builds are analyzable. And that means that all inputs are declared, all outputs are explicitly declared, and that means that your build is essentially a directed graph, so everything has a clear position in the sequence of operations. And that also means that the intermediates can be inspected, right? Because you know what is producing what. You can figure out, okay, which step actually produces this file. Can I just rerun this individual step? And I'm going to show an example with that a bit. And that together means that builds are awesome, right? Because if your build is easy to debug and it's fully incremental, and it's fast, it's parallelizable, and it's precise, then you can have great trust in your build system being correct, and you don't actually have to fight it all the time because it just, by its design, does the right thing. So I'm going to show some code here, and my disclaimer is that some of this content has been modified from the original. It has been adjusted to fit on your screen, meaning I have this example here, and I have a GitHub repository that has a complete example. The complete example is a bit longer because I added comments, and there was some complication that I have to deal with. But so this thing, my example goes about 35 lines, and in reality it's more like 100. But bear with me. Here we go. So this is a Bazel build file. And this is essentially what you, as a typical user of the build system, would interoperate with. So you have build rules or build targets. So the T's library name equals date is a build target. And it specifies, well, my name is date, and my sources, so the source files that make up this TypeScript library are date.ts. And then you have another one called user, and user contains 2 source files. So it has user.ts and nameformatting.ts, and it depends on the date build target. So these form a dependency chain. And then we have a third one, birthday card, which has the sources birthday.ts and depends on user and date. So it has a sequence of dependencies. this is a bit more elaborate than you would typically write as a user. Like typically as a user, you have individual folders being one library, and so you don't have that many targets. It's just for example a bit. But if you look at this from some distance, you can tell, well, I have a dependency from the user library onto the date library, and I have a dependency from the birthday card library onto the date library. And I also have a dependency from the birthday card library onto the user library. And so if you squint a bit, you can tell that this is actually a graph. Right? So this is actually a directed graph where you can tell, well, birthday card depends on date and user depends on date alone. And so this is how your structure, the sequence of your build gets established. Right? So Basil now knows that if it wants to build birthday card, it first has to build date, and then has to build user, and then it can build birthday card. And so the sequence is known and parallelizable. And I'm going to demo this a bit here. This is an actual picture of me demoing something, so please bear with me as I try to get this working. I'm not sure how many rakes I will find in this. So I'm here in my source checkout, and I can show you the files real quick here. So I have the build file that I just showed you. It's a bit differently formatted. And for example, I have here the date file, which is a format date function, and I have the birthday thing, and I have user from the user file, right? And so the command line, I'm going to run Bazel build the birthday card rule. I'm going to pass a special flag -s, which means that Bazel will tell me each step that it's actually executing. So we'll print out, normally it doesn't print out as much verbose information, but this will run it, this loads the package, and then it runs a subcommand to build date, and a subcommand to build the user library, and then as we expect, it has a subcommand to run the birthday card library. And if I change the user library, so I take user and add a wonderful greet function here, say, well, I'm going to log this.name, and maybe to greet, we would actually say hello. Now if I run this again, I just build birthday card again, right? So I don't actually specifically build the user thing, just birthday card, and understands, well, it has to rebuild the user library because that's the code that changed, and then also has to rebuild the birthday card library because that's a downstream dependency, right? And so this is one of the really nice things that Bazel brings. It understands the dependencies of your code and can select what to do and what to rebuild very precisely. I'm going to show you another trick, which is I'm going to drop this on here because that's too verbose for my taste, and I will just save the file again. And now if I build again, it builds the user library. It doesn't actually build the birthday card library. And the reason for that is that this change that I made here is purely internal to this library, right? So I'm changing the implementation of this library, but I'm not changing its API shape. And so I taught Bazel to understand, hey, this is only changing the implementation code here, and so I don't have to rebuild or re-type check downstream code, right? Because the downstream code doesn't care about what text is being emitted here. If I look at the API that's being generated here in TypeScript, it's the d.ts file, right? The d.ts file doesn't change if I just change the implementation. And I'm going to show you how that exactly works, how this all fits together in the Bazel code with an example. So that was the demo. So these rules are explaining to Bazel how to build code. So there's build rules that are implemented in a language that's essentially Python. It's called star-like. It's a restricted set of Python. So it doesn't allow you to do all the Python things you could do, or like call all the Python APIs that you might be used to, because it would be pretty bad if your build rules were able to delete your file system or something like that, right? So it's a restricted set of Python code. These rules are typically implemented in shared libraries, so you don't have to implement them yourself. I'm just going to walk you through it so you have a better understanding of what's going on. But typically, you would just use an existing build rule library. And so first thing first, Bazel separates your build into two phases. In one phase, it plans your build, and in another phase, it actually executes the build. And so this Python code that we're writing here is part of the planning, so of the understanding of how the build works. And then the execution is run by Bazel in a second step. So if we look at the implementation, we have, as the first thing, we have a tsLibrary object, which is a rule, right? So we say tsLibrary is a rule. Its implementation is this function called tsLibrary import that we're going to talk about in a bit. And it has two attributes, the sources and the depths attributes. And the sources is this list of files that we've just seen, and the depths is a list of labels. So sources allows files as its inputs, and depths is just a list of other build rules that we can depend on, build targets. There's also plus tools here. Tools is, again, I'm cheating a bit, right? I didn't put this on the slides, but tools essentially is the TypeScript compiler, right? Because if the TypeScript compiler would change, we would also have to rebuild all our TypeScript build targets. And so it's modeled as an explicit dependency here. So you explicitly say, well, plus these tools. And so these sources then go into our implementation. So this is the definition of a TypeScript library implementation. It takes a context object and says, well, for each of my input source files, so for context.files or sources, I produce a .js file of the same name. So I just changed the extension. And then I produce a d.ts file of the same name as well. And so I got these two things, the JS and the d.ts files as collections of files that are being produced. Interestingly, this is just declaring that a file will be created. So this code doesn't actually do it. This code just tells Bazel, hey, this will happen. And then we have a second step where we say, okay, we have these inputs to our build rule, and we have these outputs that we expect from our build rule. So we expect the JavaScript and the d.ts files to be created. And then we say, well, there's an action that will be run. It takes an executable. It takes the TypeScript compiler as the executable. It takes inputs, it takes outputs, so we're producing these outputs. And then we have the arguments here where we say, well, we're passing -- declaration, so the TypeScript compiler produces d.ts files. And then we're just passing the input source files. And as I said before, this is where I'm cheating a bit, because in reality you have to create a tsconfig.json file for the compiler, because some command line arguments that you need in here cannot be passed on the command line. But fundamentally, this is what happens. So this action that we're creating here, again, is not being immediately run. This is just telling Bazel that this action exists. And so Bazel will understand this, and if somebody depends on the files, if you want to build these files, Bazel will do that and will actually run this action. It will schedule the action and run it, but it doesn't do it immediately. So it has this planning phase and then later an execution phase. And so going on, this is sort of the recursive step in our operation here. If we have one TS library that depends on another TS library, we want the d.ts files from the other TS library to be visible to our local TS library. And so what we're doing here is we're saying, in Bazel lingo, there's a provider that we pass down. The provider has the fields d.ts for the d.ts files and JS for the JavaScript files. And in each TS library implementation, we collect our dependencies d.ts files and our dependencies JavaScript files. And then at the very end of the function, we return our own TypeScript info. So we return our TypeScript info where we say, well, we're producing this d.ts, including the transitive d.ts, so everything from our dependencies. And we're producing this JavaScript, including the transitive JavaScript from our dependencies. And these are dependency sets, so dep set stands for dependency set, so they're being deduplicated by the compiler automatically, or by the Bazel build system. And so if we combine this, the TS library in the build rule declares your sources and your dependencies in your system, and then the Bazel build rule implementation declares how to generate these outputs, so how to run these actions or what actions exist. And then Bazel analyzes the build and then later on executes the steps that cause these actions to be run and then actually cause your output files to be created. And that's really useful because Bazel now has full knowledge of your inputs and outputs, and so can do precise caching. So if it, for example, finds that you have a TS file that hasn't been changed since the last build, it will understand with confidence, yes, this file hasn't been changed, so I don't have to rerun this TypeScript compilation action. Also, because we have a complete understanding of the dependency structure of our project, we have the ability to efficiently schedule these actions, right? We say, well, my computer has 8 CPUs, and so I might decide to run 8 TypeScript compilations in parallel and in correct sequence, so I know that actually everything is still running correctly and working out. And this actually allows us to do some other really neat things, like in the Angular project, we're doing remote execution. So if you have all the inputs precisely specified and all the outputs specified, what you can do is you can actually go to a cluster and say, well, you know, I only have a small little laptop here, but I might actually be using CPUs in the cloud to execute these build steps. Because I know what the inputs are, I know what the outputs are, and so I can just send the entire build job to this remote system, essentially. And we were using that in the Angular project with great success to improve our build performance. And so going back to this slide once more. So this is about 30 lines of code, and as I said, I'm cheating, so it's about 100 lines of code. But this is all I'm doing here, right? So this is all I'm doing. I'm only telling Bazel the structure of the code and how the dependencies are. And so by virtue, I've showed you this example of how I changed the implementation of user.ts, but not the API of user.ts. And Bazel doesn't know anything about TypeScript in the first place. It has zero knowledge about it. But because it knows that the d.ts files didn't change, it knows that it doesn't have to rerun the action downstream. And so we're abstracting away the concept of how the build works and how the steps fit together and what the inputs and outputs are, and using files for that on the file system as the simplest mechanism. We're separating that from the actual TypeScript operation, right? So the TypeScript compiler is a really complicated beast that somewhere runs under this, but Bazel doesn't have to know anything about it because it just looks at the files, it inputs and outputs, and can base its decisions out of that. And so that's the real beauty of this, that you're able to write relatively succinctly, right, in a really small piece of source code, these concepts down, and then actually have them later on work everywhere. That's really beautiful. Okay, so the benefits, as I said, we're separating concerns, right? So we have the build rule that's pretty simple, actually. It doesn't need to know anything about the compiler or about the type system or anything of these complicated things. And because it's enforced by Bazel that these things run in isolation and in a sandbox, so they cannot actually interfere with each other or read files that were not declared, we can be certain that our builds are reproducible, right? And they are safe and understandable, and so we can actually rely on the fact that these things work correctly. And we get precise caching, so we get incremental builds and tests too, right? Of course, if the tests essentially are a function that takes input files that are the test to run, and then it produces output files that are just the test results on disk, then you have the same effect, right? You know exactly that the inputs haven't changed, so you don't have to rerun the build, even if the user has to test. And again, also this enables really interesting use cases like remote execution, cached builds, this kind of stuff. With that, I'm running quite a bit early. Didn't find enough rakes to step into on my way through the demo, I think. But here's a bunch of links. So we have the slides link for the Connect 2018 Bazel. These slides. Then I have a link to the Bazel homepage. And the example code from these slides, the TypeScript Bazel-TypeScript-example is there for you to take. Please do not use that code in production because it's terrible. Like it's a very simple example, right? And so we have a proper implementation of these rules that have a bunch of other neat features like keeping a TypeScript compiler running in the background, warm, so to say, and so not having to restart the TypeScript compiler all over the place, which makes the builds a lot faster, right? So if you've seen my example, you might have noticed that it takes a couple of seconds to build a rule here, and in reality, it should be a couple of 100 milliseconds, so it's a lot faster. So rules TypeScript is the proper implementation of the TypeScript rules, but there's also rules Angular, so there's a implementation of the Angular specific build rules using the Angular compiler. And then this is Alex's code. Alex has an example of Angular and Bazel and the CLI working all together with a nice demo. So with that, I would say thank you for your attention, and that's it.